Alright guys, what I'm looking to do is go through a few of the problems. So when I'm doing this, if you want to follow along, you should probably have the problems either printed out or on the computer screen adjacent to it so that you can read them along while I go through them. I'm going to go through a few of the kinematics problems right now. I'm planning on going through problems 1, 3, and 6 in this video. We'll see how long that takes. Before I even get started, problem 1, something we need to make note of here. It's the concept of arc length. So basically in problem 1, you're going to have a wheel and this cord wrapped around it, and the cord is going to unwind. So basically what's going to happen is that there's string wrapped around a circular object here, and as it starts to unwind, what you're doing is you're releasing linear distance that's attached to this circular object here. So if I make a little mark here, this point here, if this circle right here is looks to me about 5 centimeters, so the radius is about 0.05 meters, that is. And then what would end up happening is that as this thing starts to rotate, it's moving a linear distance. So if I start to rotate it, let's say counterclockwise, 90-degree rotation, what we've done is we have covered this linear distance right now. That's how much the object has moved. All right, so if I wanted to calculate that, that would be a delta theta of 90 degrees, or pi over 2 radians. And since the arc length S is equal to delta theta times r, we can do pi over 2 times 0.05, and I need to get out of exact mode and into approximate mode. It's going to give me my meters here, and then what I get for S is about 0.078 meters, which is easy enough to see. Now let's say we start here again and we do one full rotation. How much has this object moved? It's gone the whole circle. So basically it's gone the circumference of the circle. But let's say that it went again and kept rotating more than that one rotation. Let's go to about there. So it's gone the circumference of the circle and then some. Basically, we have a delta theta here of, when we did one rotation, that's 2 pi radians, and we did a half rotation, that's basically 3 pi radians. Delta theta here is 3 pi. R is still 0.05. If you were looking at how much arc length we have there, arc length can go beyond the single circumference of the circle for a case like this. So if I was calculating S here, it's 3 pi times 0.05, and what I get is that this thing has moved 0.471 meters, or almost a half meter, in that rotation and a half. So that's how we want to lead into problem 1, because if you take a look at problem 1, we've got a wheel. Its diameter's 3 centimeters, which means its radius is 1.5 centimeters. Right? So there's our wheel. R is 1.5 centimeters, or 0.015 meters. Always want to be in meters here. And then there's a cord wrapped around it. And what ends up happening is that the cord is released. Basically, it's kind of like a paper towel roll that's being unwound. What's going to end up happening is that the cord just keeps traveling down as it's released. And you want to think of this as how much distance that, the point that's initially here just keeps spinning around. 4 meters. That's your arc length value, essentially. S here equals 4. From that, we can figure out how many rotations occurred, because we have the radius and we have S. So we do S equals delta theta times R. We can get delta theta right now. 4 meters here, delta theta is unknown. R, 0.015 meters. 4 divided by 0.015. I get a delta theta of 266.67 radians. And how many rotations would that be? If I divide that by 2 pi, we get 42.44 rotations. Alright, so we know what delta theta is. We can report it in radians, or we could report it in rotations. Next part of that question says, well, we're given the angular acceleration here. How many rotations would occur, and how long will it take for it to unwind? So we need to solve for t here. This is a kinematics problem, essentially. Basically, we're given an alpha value. Alpha is our angular acceleration. It's 2 radians per second squared. We start from rest, so omega I is 0. And delta theta is 42.44 radians. Keep in mind this is in radians per second. Rule in kinematics. Think back to this September, is that if we have 3 out of 5, we have all 5. So we can use a kinematics equation to get there. If we want to solve for time, I'm probably going to go with, I'm going to guess this one. Delta theta equals omega I t plus 1/2 alpha t squared. That's 0, so that's going to be kind of easy to solve. 42.44 there, 0 there, 1/2 2 t squared. See if it all works out, see if we get what we do on the answer key. Yeah, I did not, but did I screw up somewhere? What did I do wrong? Crap. 42.44. One half 2 square time. What do I get? 6.5 seconds. No, that's what I did wrong. I'm an idiot. I'm in rotations here. I need to be in radians. 266.67 radians. Now I'm willing to bet it's going to work out. You know, if I knew how to edit the videos, I'd totally cut that out and act like I knew what I was doing. 16.33 seconds. Alright, so, you know, we're about 7 minutes in. Let's try and get through the other ones quickly. After that, I want to go through problem 3. You got a pitcher. He's going to throw the ball. Pitchers, they put spin on the ball. So what's going to end up happening is that the ball's going to spin quite rapidly. And now this is it's spinning at a uniform rate, because we're told that it has a cycle of 300 hertz. If you remember back to uniform circular motion, that's the frequency. That's how many cycles occur per second, or how many rotations occur in 1 second. Basically, what we're going to need to do is we're going to need to find out, well, how long does it take to get from the pitcher who throws it all the way to the catcher who's waiting for the ball. And I think we're given a linear distance there of 30 meters. You got 30 meters between here and here. And we're told that he threw it at 40 meters per second. So let's go back to motion in 1D. Delta x VIT. You know what? There's no acceleration here. So simply velocity times time equals displacement here. So 30 equals 40 times t. 30 divided by 40 is 0.75. That's how many seconds it takes for the ball to get from here to here. Now that's important because we have 300 hertz. Remember, 300 hertz is basically 300 cycles or rotations per second. So we can get exactly how many rotations there are going to be here. If we just take the 300 rotations per second, multiply it by the 0.75 seconds that elapse here, seconds are going to cancel out here. And 300 times 0.75 is 225 rotations, which is exactly what we were looking for. Alright, so pretty easy problem there once you put it into perspective and figure out how to get the answer there. Last problem that I want to go over in this video, it says, you know, you got something that is undergoing a change in angular velocity as a function of time, and it's a uniform acceleration problem. So the graph of omega versus t looks like this, but you're only giving it out to 5 seconds, right? So, what ends up happening is you got the data all the way up to there, and what you need to do is you need to extrapolate. What's it going to be out to 8 seconds? So basically, if we start at the 3 seconds, what you should see right now is that this thing increases its angular velocity by 3 radians per second every second that goes by. So if this is the 3 second mark right here, and then you have 4 seconds right here, this point right here is at 3, and then this is the 5 second mark, and then we're at 6. So go out to 8 seconds, and you're going to get 9 more. So basically, you're going to get out to here, and you're going to be looking at a graph that goes from 0 to 15, right? From 3 to 8 seconds. And what we need is we need the area under that curve. So, should be pretty simple. Area is 1/2 base times height. So we have 1/2. The base is 5 seconds. The height is 15. I get 37.5 radians, and that gives us our displacement delta theta, which is the area underneath that curve. More problems to go later.